Hello everyone, and welcome to the lecture on Breadth First Search Algorithm, or BFS. So in this lecture, we're going to get an overview of that BFS algorithm, and we're going to continue to build off that example of that word ladder problem. So what we want to know now is how can we find the shortest solution to the word ladder problem? We were able to build out that graph efficiently using that buckets method, but now what we want to do is actually find the solution to it as we traverse the graph or go through the graph. The graph algorithm we're going to use is called Breadth First Search Algorithm, or BFS. It's one of the easiest algorithms for searching a graph. It also serves as a prototype for several other important graph algorithms that we're going to study later. Of course, as an extra resource, there's an MIT Algorithms and Data Structures course. It's part of MIT's open courseware, and I encourage you to check it out. Here's the link so you can go to the resource section, download this presentation, or just copy and paste this link into YouTube. And I think you'll be really surprised on how well you can follow along, given that you're going straight into the middle of an MIT Data Structures and Algorithms course. Pretty much you can jump right in. We've covered a lot, and I encourage you to really use this course as an extra resource for understanding algorithms and data structures. Just keep in mind that it's really more on the theory and more basic computer science ideas, while in this course we try to emphasize which ideas are important for interview situations. So just keep that in mind, but it's a really great resource. I definitely encourage you to check it out. They have the whole playlist, and you can also check out additional homework assignments that go along with that on MIT OpenCourseWare. Again, it's a great resource, and you can jump right in. You'll really notice how you can understand already everything that they've been talking about, even though this is basically halfway through their semester. Okay. Moving along, let's talk about BFS. So given a graph G and a starting vertex S, what the BFS algorithm does, it proceeds by exploring the edges in the graph to find all the vertices in G for which there is a path from S. The remarkable thing about the BFS algorithm is that it finds all the vertices that are at distance k from S before it finds any vertices that are at distance k plus 1. So one good way to visualize what the BFS algorithm is doing is to imagine that it's building a tree one level of the tree at a time. And what the BFS algorithm does, it adds all the children of the starting vertex before it begins to discover any of the grandchildren. As we go along and explain the BFS algorithm and the example code, we're going to keep track of its progress through coloring. So BFS is going to color all the vertices white, gray, or black. All the vertices are initialized to white when they are constructed. A white vertex is an undiscovered vertex. So as we go through the graph, if it's white, it means we haven't discovered it yet. When a vertex is initially discovered, it's colored gray. And when a BFS has completely explored a vertex, then it's colored black. This means that once a vertex is colored black, it has no white vertices adjacent to it. A gray node, on the other hand, may have some white vertices adjacent to it, indicating that there's still additional vertices to explore. And we'll actually see this basically diagrammed out later on in this lecture. So what the BFS does, it begins at the starting vertex S, and colors start gray to show that it's currently being explored. Two other values, the distance and the predecessor, are initialized to 0, and then none, respectively, for the starting vertex. And then finally, start is placed on a Q data structure. The next step is to begin systematically exploring the vertices at the front of the queue. So then what we do is we explore each new node at the front of the queue by iterating over its adjacency list. As each node on the adjacency list is examined, its color is checked. If it's white, the vertex is unexplored, and then 4 things are going to happen. If the vertex is unexplored, we have 4 things that are going to happen. The new unexplored vertex, which we'll call NBR for neighbor, is then colored gray. The predecessor of neighbor is set to the current node, current vert, or current vertex. The distance to neighbor is set to the distance to the current vertex plus 1, since you had to go an additional edge. And then the neighbor is added to the end of the queue. Adding neighbor to the end of the queue effectively schedules this node for further exploration, but not until all the other vertices on the adjacency list of that current vertex have been explored. So let's take a quick look at what some example code may look like. So you have a new unexplored vertex, NBR, that could be colored. So we'll start from the very beginning here. We have BFS, it takes in a graph and a start. You can say start set distance, start set predecessor, and we'll look at that. Those are just additional methods on the vertex. that we're using to essentially visualize what the BFS is doing. So we begin at the starting vertex S, and then the colors start gray to show that it's currently being explored. Then the two other values, the distance and the predecessor, have been initialized to 0 and none respectively for the starting vertex. And then finally, the start is placed on a queue. So you have start and queue over here. The next step is to begin to systematically explore the vertices at the front of the queue. We explore each node at the front of the queue by iterating over its adjacency list. As each node on the adjacency list is examined, its color is checked. Then if it's white, which happens at this step, we do a couple things. The new unexplored vertex neighbor is colored gray, so we set color gray. The predecessor of neighbor is set to the current node. The distance to the neighbor is set to the distance of the current node plus 1. And then the neighbor is added to the end of the queue. Again, by adding neighbor to the end of the queue, you've effectively scheduled this node for further exploration, but not until all the other vertices on the adjacency list of the current vertex have been explored. So this is just a quick example code. I know we didn't actually go and create a few of these methods, but just keep in mind, it's just to help you out what the code would look like for the diagram and explanation we're about to see. So now let's take a look at how that BFS function would construct basically the breadth first search tree corresponding to the graph here. So what we're going to do is start from full and take all the nodes adjacent to full and add them to the tree. So if we go ahead and visualize that, we start with full, take all the nodes that are adjacent to full and add them to a tree. The adjacent nodes here include pool, foul, and cool. Or foil, excuse me. So pool, foil, foul, and cool. Each of these nodes are added to the queue of the new nodes to expand. So here you have a queue of the new nodes to expand. So here we are on the in progress tree along with the queue after this step. In the next step, what the BFS does is it removes the next node, which is pool in this case, from that front of the queue and repeats the process for all of its adjacent nodes. However, when BFS examines the node cool, it finds that the color of cool has already been changed to gray. This indicates that there's a shorter path to cool and that cool is already on the queue for further exploration. The only new node added to the queue while examining pool is then poll, P-O-L-L. And the new state of the tree and queue is then shown here. And what may be helpful is to open up this graph picture and see it along as we go through the BFS search. But after this is the second step. Basically, the next vertex on the queue is foil, F-O-I-L. So what does that mean? That means the only new node that foil can add to the tree is fail, F-A-I-L. And as BFS continues to process the queue, neither of the next two nodes adds anything new to the queue or the tree. So here in this figure, we see the tree and the queue after expanding all the vertices on the second level of the tree. So now what I encourage you to do is continue to work through that algorithm on your own so that you're comfortable with how it works. So what you should really be doing now is definitely checking out that MIT video I linked earlier, and then trying to see if you can continue with this algorithm until you get to Sage. And what it should look like is this figure right here. So I encourage you to take this figure and see if just basically mentally you can build this out as your path as you construct the tree in your mind using BFS. And if you want further explanation of BFS, then you can definitely reference that video that I mentioned at the beginning of the lecture. So it's a bit of a complicated topic to formally write out, but the idea is actually kind of simple. So let's quickly recap what the BFS is actually doing. It starts at a vertex S, and then if we go ahead and jump to that code listing, so here we take in G and a start. So we start at a vertex S, and then what we're going to do is then color that start variable gray to show that it's currently being explored. So remember, we have three colors here: gray, white, and black. All the vertices are initialized to white when they're constructed. So that means a white vertex is an undiscovered vertex. When a vertex is initially discovered, it's colored gray. And then when a BFS has completely explored that vertex, then it's colored black. And again, once a vertex is colored black, it has no white vertices adjacent to it. And then the gray node, on the other hand, may have some white vertices adjacent to it, indicating that there's still some additional vertices to explore. And so in this coding list, the distance and predecessor are initialized to 0 and none for that starting vertex, and then we place that start vertex on the queue. Then the next step is to begin to systematically explore the vertices at the front of the queue. And we explore each new node at the front of the queue by iterating over its adjacency list. So again, refer to the adjacency list lecture for what's actually happening when we iterate over it. But basically, as each node on the adjacency list is examined, we're going to check its color. If it's white, that means that vertex is unexplored, and 4 things are going to happen. That new unexplored vertex is then colored gray, because we're there now. The predecessor of that vertex, that NBR, that neighbor, is set to the current node, which is the current vert or current vertex variable. The distance to neighbor is set to the distance of the current vertex plus 1, and then neighbor is added to the end of the queue. By adding neighbor to the end of the queue, we've effectively scheduled that node for further exploration, but not until all the other vertices in the adjacency list of that current vertex have been explored. That way, if we reach the end, or the target, we'll reach it first. So what's the amazing thing about the BFS search solution is that not only have we solved the fool to sage problem, so given that graph, find that path, but we've actually solved many other problems along the way. Now we can start at any vertex in the BFS search tree and follow the predecessor arrows back to the root to find the shortest word ladder from any word back to fool. So up next is the Knight's Path problem, and that's going to be our introduction problem to depth first search, or DFS. So what should you do now? You should definitely go through that MIT lecture, listen to it. It's about 40 minutes long, so it is quite a time commitment, but you'll be able to jump right in, understand what they're talking about, and get a chance to see how this topic is taught in basically the best technical university in the world. And you'll be surprised at how well you'll be able to jump in, and you'll know pretty much all the terms that they're talking about, as well as the notation. Then, once you're done watching that, come take a look through this presentation and make sure you really understand BFS and see if you can follow through those diagrams. Okay. Thanks everyone, and I'll see you at the next lecture where we discuss that Knight's Path problem and get an introduction to DFS, or depth first search. Thanks, I'll see you at the next lecture.